Hello, my name is Kylie Bivens. Welcome to the 7th seminar in our RSI seminar series. It's a part of the Advanced Transportation Technology Seminar Series and is sponsored by the Roadway Safety Institute. This seminar is open to anyone interested to learn more about transportation, but it is also being offered for credit here at the University of Minnesota. Students in the course, if you have questions, please save them until after. And you're welcome to ask me questions afterwards. As always, the seminar is being streamed live on YouTube Live. And for our remote viewers, please type in your name to the chat box with your affiliation and the number of viewers so that we can report it to the US DOT. Also for the live audience, please hold all of your questions until the end, and we will get to them at the end of the seminar. And also note that there is a 30-second lag for our online viewers. Thank you.
All right. Well, thank you, Kylie. It's my pleasure to introduce today's speaker, Professor Gebre-Egziabher. I think I pronounced that close to being right. All right, an associate professor and currently doing duty as director of graduate studies, I guess, in the Department of Aerospace Engineering and Mechanics here at the UMN. His research focuses on navigation, guidance, and control of aerospace and ground vehicles. Okay, applications of his work have included development of attitude determination systems for satellites, high accuracy navigation of aircraft, and evaluation of operations of small autonomous aerial vehicles, okay, in the National Aerospace System. You didn't come here to listen to me, so I'll turn it over to our speaker here.
All right, thank you very much for that introduction, and thank you everyone for being here, taking some time out of the afternoon to be here and listen to this talk. The title, again, as you can see of the talk here, is looking at current and future applications of what we call GNSS. Most everyone is probably not familiar with that term, synonymous with GPS, but I'll kind of make that definition clear. So that's what I'm going to talk about today, applications of GPS in navigation and guidance for vehicles. And it's going to be more on the GPS side than the application sides. And I'll tell you what I'm trying to get across in this talk. So, global navigation satellite systems are systems that provide position and timing globally for users, and they're based on using signals from satellites. And the one that most everyone is familiar with, let's see if this laser pointer works, is the GPS, which is a GNSS that's operated by the United States Department of Defense. All right. Now, there are a couple of other ones that are, there's actually one other GNSS that's operational right now. It's the one that's operated by the Russian Federation called GLONASS, and then there are a couple of other ones that are coming online in the near future. All right. So the system has been around. GPS has been around since, I guess, it was declared operational in 1995, and it's being used for all kinds of things. All right. So what I'm going to do is give you a couple of examples of things that it's been used for, and then I'm going to bring up some cases where there are users that are kind of shying away from using it for applications, and we'll use that as a stepping stone for what I want to talk about today. So applications that GPS now is being used standard for, for example, is transoceanic navigation of aircraft. So before the 1990s, when aircraft went over the oceans, they did not use GPS, they used something else for navigation. So the navigation across large spaces of water was not a trivial problem. But now that's a trivial problem with GPS or with GNSS. Navigation of ships coming in and going out of harbors. Again, for those of you that are old enough to remember the Exxon Valdez, that kind of a mishap these days are, you can't say they're not going to happen, but they're less likely with GPS being around, giving you precise positioning within channels. And it's used quite a bit with ships. Another place where it's used quite a bit is in farming applications. So here you see a John Deere tractor with a John Deere GPS receiver up there. Actually, it would be Navcom, but it's a John Deere company. And they use it for autonomous guiding of these vehicles for doing precision plowing and things like that. So it's a standard thing. It's being used quite a bit even in those applications. And then there are quite a few other applications that people don't think about where GPS or GNSS are being used quite a bit. And one of them is timing of banking transactions. It's not only a positioning system, it's also a timing system. So it's become the de facto heartbeat for anything that requires timing or precise timing. And banking transactions are one of the things where if you trace them back, you'll find that GNSS or GPS time is being used for that. Another place where it's being used heavily is synchronizing power grids for making sure that loads like frequencies from different power generators are all matched in frequency. So it's become basically a utility, very much like light switch or the water faucet, and we rely on it without knowing that much. So it's become pervasive, all right? But I'm using that as a setup to what's coming down the pike these days. There's a lot of other applications that are showing up where you would think GPS or GNSS would be the primary sensor that you would choose for it, but it turns out that there are some users that are shying away from it. So for example, if you take a look at autonomous cars, in this case I've got the Google car here, there are a bunch of other ones that are being developed. In some of these cases, you would think that GPS or GNSS would be the primary sensor that's being used for navigation. It turns out that it isn't. Instead, other sensors like LiDARs, radars, odometers are being used. And while GPS is there, it's not central to some of these applications. So when I put this talk together, what kind of motivated it was the comments that I was hearing from persons working around guidance and navigation, or guidance and control primarily, talking about failures or faults of GPS and why they're not using it in certain systems. So this is an example of a case where it's not used. And if you hear the complaints that people have against GNSS, you could kind of put them into two categories. One, it's not accurate enough. It's not accurate down to the centimeter level. That's complaint number one. And complaint number two, it's not robust or it's not reliable. And the point of this talk, what I want to do is I want to show or talk about these two aspects and show you that there's some truth to them, but they're not entirely true, right? So we can get centimeter level positioning and we can get robust and reliable positioning. It's just that it's not at a point these days where it's cheap and inexpensive, but it might be very, very much so in the near future. So that's my goal, is to kind of show you why these two statements are not entirely true, but also tell you why it's difficult to get centimeter level accuracy with GPS or GNSS and what the issues that need to be solved in getting it down to that level are. All right, so just in case you're not convinced that GPS is being used for centimeter level type of positioning, here are a couple of examples where it's actually being used for that. Surveying is one of them, right? So these days, a lot of surveyors use GPS-based or GNSS-based surveying systems, and they get centimeter level accuracy out of it. So it does provide centimeter level, if not millimeter level accuracy in some instances. All right, so here are some figures that I got from Brian Davis here in the ME department, showing applications where they were doing some, I guess you would call this high accuracy mapping of road infrastructure. And part of the sensor that was used, it was not only GPS, but a part of it that was used was a high accuracy GPS receiver that allowed them to lay down the location of these markers on a street very accurately. There are all kinds of interesting things that you could use high accuracy positioning for, like driver assist systems. I think next week's talk is going to be on something related to this, so I won't say much about that, and it's definitely not my area anyway. Another place where it's used quite a bit is asset management or tracking of assets. And in these kind of applications, again, you need very accurate centimeter level type of positioning, and GPS does provide that, right? Other applications more close, near and dear to my heart are applications in precision agriculture where we're trying to use small unmanned aerial vehicles or drones to basically survey fields. In our case, one of the projects we're looking at is trying to figure out infestation levels of aphids on a farm field. And in that case, being able to look at an image and know exactly where it is based on where the aircraft is a very useful thing. And while this can't be done reliably, it can be done using GPS. And again, it requires centimeter level of accuracy, and that can be done. But again, not very easy. It's not a real-time process. It's more of a post-process type of a thing. So the point is, you can get centimeter level position accuracy with GPS, and you can get it in some instances reliably. So what I really want to do through this talk is answer these two questions. One, why is it difficult to get high performance centimeter level accuracy using GPS or any of these GNSS and transportation applications? Right? You can get it, but it's not easy, and I'll explain why. And then the second thing is what's happening? What kind of new developments are occurring to make this become easy and always available in the future? Again, I've been playing around with GPS or GNSS since, 1996 now. And it's amazing how much changes have happened with this technology over that time. Things that didn't look like they were going to be possible have become possible. So I'm convinced that it's going to be some time, but we will be able to get centimeter level positioning with GPS or GNSS accurately. But there are challenges. And what I'm going to talk about is what are those challenges and what are the fixes that are coming down the pike to make that happen. All right? So to do that, I'll have to start off with giving an overview of how GPS works. Some of you in this room probably know this fairly well, so it might be boring for you, but I like to set the groundwork so we understand where the challenges are that prevent you from getting centimeter level positioning with GPS. So I'm going to use GPS as a prototype for any of these global navigation satellite systems and talk about it, but anything I talk about GPS maps over to the other systems that only one other one is operational, the others are going to be coming in the near future. All right, so first of all, it's a satellite-based system designed around 24 satellites. Currently, there are about 31 of them in orbit. There are a lot of people that like to call these, that want to call them GPTS because positioning is not only the thing that comes out of them, they're also timing systems, they're accurate clocks. And GPS provides two levels of service. The standard garden variety of service that everyone has access to is what's called SBAS. And the accuracy that it gives you are on the order of what you see here. So on the order of about 5 meters accuracy and about 7 meters in the vertical, and timing accuracy down to 30 nanoseconds. Now there's a second level of service called PPS, or Precise Positioning Service. It's controlled access. It's only available to authorized DoD users that are using GPS, and we'll talk a little bit about that and see how that access is controlled. But this is basically what GPS is. So nominally, it provides something on the order of meters. So this is not quite centimeter level accuracy. So how do you get down to the centimeter level accuracy? All right, so to explain that, let me say a little bit about how GPS does the position calculations. Again, this might be a little bit of a review to most. What you need to get a position solution and a timing solution is 4 satellites in view at a minimum, because your problem you're solving is 4-dimensional. It's X, Y, Z position and time. And time is critical because the way you determine these ranges to each satellite is by measuring how long it takes the signal to leave the satellites and get to you. So the satellites put a timestamp on the signal as it leaves. You receive it. You look at the time at which you received it. You multiply that by the speed of light. That gives you the range. So all it takes is a microsecond worth of error in that measurement, and that translates to about 300 meters worth of error. So you need to know time precisely. So that's the 4th unknown that has to be solved for. So that's why they're timing systems. And again, it just turns out to be a simple, nonlinear, coupled set of equations. Solve those, and you get your position solution and time. All right, so to understand how that's done, a little bit more about the signals. So I'm putting the word legacy here, and I'm using that because I'm going to tell you in maybe another 15, 20 minutes that there are new signals that are going to be coming from the satellites in the near future that are going to allow us to do what I'm talking about, centimeter level positioning. But right now, let's talk about the legacy. So the legacy system they transmit 2 signals. One of them is called L1, which is at 1575 megahertz. And this is the signal that carries the information that everyone that has a GPS receiver uses as this particular signal, is L1. The second signal, called L2, which is at a separate frequency, is the one that if you do not have authorization, you can't access it. So it's controlled by it's controlled access only to DoD authorized users. But these are the 2 signals that were being transmitted by GPS since it became operational in 1995 until recently. All right, the signal itself looks like this. And again, a little bit of background here too, so you could appreciate where we're going or how we're going to get down to the centimeter level positioning. If you take a look at the signal, it consists of 3 components. There's the RF carrier that brings the signal down. So if you go back to the previous slide, that would be these guys here, L1 and L2. All right, so there are 2 radio frequency carriers. And on top of those are superimposed 2 pieces of code or digital messages. One, which is called the code or the CA code, at least for the one that civilians use, is basically an identifier that identifies each satellite and tells you which one is which. And then the second one is actually data that tells you information you need to be able to compute your position and estimate time. All right? So in a GPS receiver, your common garden variety GPS receiver, that carrier part of it, as soon as it gets to the receiver, it's more or less it's wiped out, and what's left is the code, these two parts of the signal. So you will hear people that are in the field with GPS or that area, you hear them talking about code phase positioning. What they're talking about is the garden variety positioning that relies on these two signals. As you're going to guess, when I talk about the precise positioning, it's based on using that RF carrier in a smart way. All right, so in transportation applications, there are all kinds of things that we're concerned about. And when you evaluate the use of GPS in transportation applications, there are different metrics by which you measure it. The one that we're going to focus on right now is just going to be accuracy. We're interested in getting down to centimeter level of accuracy. And what does that mean? Well, we're talking about the 95 percentile errors or the 2 sigma type of errors. So we're going to look at how you can get down to centimeter level of accuracy using GPS and what are the challenges. All right, so accuracy. So instead of telling you how you get down to that accuracy, let me start by telling you why you can't get the accuracy and what are the things that actually cause the problems with getting GPS accuracy. And particularly in transportation applications, the biggest problem is this, what I show here, which is called multipath. Multipath is basically a signal gets broadcast from the satellite. There's a direct signal that comes to the user. So you measure the time of flight of that signal, that tells you the range of the satellite, you figure out your position. However, if there are structures in the vicinity of you, then they will reflect signals off of them. So what you're going to get is reflected signals that make it look like the satellite is actually farther away than it really is. So if you have reflectors close by, they will cause problems, and that's called multipath error. And the problem with multipath error, it turns out to be slowly time varying, and there's really not much you can do. There's things you can do about it, but it's really hard to deal with. You can't average it out, for example. So it's a big problem. So if you're talking about, for example, automotive navigation applications where you're trying to get really accurate positioning and you're going down in a downtown area, multipath is going to be a big problem. So I'm not going to talk about how we deal with multipath. That's not my area, but there's a lot of work going on trying to get rid of multipath or be able to deal with multipath. But that's one of the big sources. So in the absence of multipath, what are the other things that actually cause your signal not to be very accurate? There are two other problems. They turn out to be what you would call channel errors or propagation errors. The signal leaves the satellites. It goes through two layers of the atmosphere, the ionosphere and the troposphere. And both of these actually cause delays in the signal. And the ionosphere actually, not only does it cause a delay, but it could cause refraction, if you will. It makes the signal bend. So these two error sources together contribute to the inaccuracies that you see in the GPS position solution. So in the case of the ionosphere, that error, we'll call it I sub rho, depending on what time of the day it is, it depends a lot on solar activity, for example. Right? The ionosphere is basically a soup of electrons, if you want to think of it that way. And depending on how much sun has been hitting it or how much solar activity is going on, those errors could be as high as 15 meters. All right? So, however, the other one that affects it is the troposphere. That's basically the atmosphere that we live in, the moisture content of the air. And that could introduce errors as large as 25 meters. However, most GPS receivers have built into them models to account for these errors and try to remove them. And by the time you correct those errors, you're down to about 10 meters or so on the ionosphere and about another 10 centimeters on the troposphere errors. So if you don't get rid of all these errors, you still are not going to get down to that centimeter level positioning. So they could be reduced further by two tricks. One is if you use two frequencies to measure your range to the satellites, then you could actually back out the ionosphere error because the delay that's introduced by the ionosphere is a function of the frequency of the signal that's being broadcast. So if you have two frequencies, you could back that out. And hence, users that have access to the two signals that are coming from the GPS satellites, the one that all civilians could see and the other one that's only accessible to DoD authorized users, if you have those two, then you could go ahead and actually estimate the errors that are introduced by the ionosphere and reduce them down to about a meter level of error. Right? So the common garden variety GPS that civilians use, you do not have that second frequency. At least you didn't have to until recently. So you had to figure out a way of getting rid of that 10 meters worth of error somehow. Another way to get around it is a technique called differential GPS, and I'll talk more about that because that is how we get down to the centimeter levels of accuracy. All right, so what is differential GPS? It's a trick, if you will, that allows you to figure out what the errors introduced by the ionosphere and troposphere and other things that are called common mode errors are. And the idea is deceptively simple. The idea works by you place a GPS receiver at some point that's known. You call that a reference station. Now, if that reference station is in close vicinity of someone that's trying to figure out their position, the errors that are affecting the accuracy, for example, the ionosphere error, will be kind of the same for the two. So since this guy is at a known position, you could back out and reverse what the ionosphere error should have been and then broadcast that information out to the local user. Right? So it works well if someone is close to the reference station. It doesn't work very well if a user is far away because, again, the errors that are causing the inaccuracies are not going to be common to both, so it doesn't work very well. But this is differential GPS. There are different ways of actually getting it to work. There are different formulations of it. And with differential techniques, we could get those errors down on the range measurements down to about 20 centimeters. So slowly but surely we're beating down those errors till we get them to become really, really small. This formulation of differential GPS is what one would call a ground-based augmentation system, or a GBAS. And what it really means is that I have a reference station on the ground and it's broadcasting out corrections to local users on the ground. There are different formulations of these differential systems. So in the United States, for example, there is a differential system that's providing corrections without, most receivers these days could actually use these corrections. It's a differential correction system operated by the FAA called WAAS, or Wide Area Augmentation System. And it has reference stations shown here. And all of these stations collect all their data and they send it to a master control station somewhere out in this case, it's out in Atlantic City. And those signals get broadcast up to a triplet of geostationary satellites, which broadcast down the corrections. So this is what one would call a space-based augmentation system. But either way, both of these, the basic idea is by looking at common mode errors, I could reduce the errors down to now sub-meter accuracy. So these days, most GPS receivers you could get off the shelf will have the ability to process WAAS signals. So you should be able to get down to sub-meter, but not quite centimeter level of accuracy using these, as long as you're not dealing with multipath type of errors. All right, so now, what if you want to go lower, down to the centimeter level accuracy? Then you have to start going to different processing techniques. And the one that I'm going to talk about a little bit more in this talk and mention to you that it gets you down to centimeter level, but also show you why it's a hard problem, is what's known as carrier phase differential GPS, or sometimes it's referred to as RTK, or real-time kinematic GPS. And in this case, you're using the signals in a way that the original designers really did not intend the signal to be used, but it works. So instead of looking at the code, right? So the previous slides I showed you that there's the carrier and then there's code modulated on it. In this case, you're looking at the raw carrier signal. And the carrier on the L1 signal has a wavelength of about 20 centimeters. And you can measure that wavelength down to a millimeter level of accuracy. So a GPS receiver could track these signals, and as it's tracking them, it knows exactly where it is in each cycle. And it knows that fairly precisely down to the millimeter level. So in theory, if you knew how many cycles there were between you and the satellites that are broadcasting the signal, then you should be able to get your range down to a millimeter level of accuracy. It turns out that it's very hard to estimate how many full integer cycles there are between you and the satellites. So normally what is done is we go into a mode where a reference station works with a user where they exchange information and they calculate the difference between the carriers, and that way they remove a large portion of the integer number of cycles. And if you work that out, then you should be able to get down to the centimeter, if not millimeter level of accuracy. And that's what surveyors use, by the way, and that's the technique that gets you down to the millimeter level of accuracy. All right? So you can get down to the millimeter level of accuracy, centimeter level of accuracy. What is the problem? Why is it not used widely? Why is it not used in transportation applications? It's used in transportation applications, but it's not used widely because of a couple of issues. Right, so what are the challenges? So if you look at the problem in a mathematical way, and I'm not going, this is one of two equations that I'm going to, well, not too many equations, so don't worry about this equation too much, except that I'm going to point out one aspect of it. The equation that you solve for getting your position, so this relative range between the reference station and the user, that's XUR, is solved by inverting this equation. This here is basically the difference between what this reference station was observing and what the user is observing. And then there's a bunch of other stuff on the side. This is just noise, and this is the number of integer cycles between the reference station and the user. So it turns out to be an integer least squares problem, meaning that standard numerical techniques you'd use to solve linear problems like this will give you a solution for these that are not integers, but numbers that are real numbers, that are, float numbers. So to get the full accurate centimeter level positioning out of this, you have to actually solve the integer least squares problem, and it turns out to be nothing more than a search problem, right? So the way that works is you come with a rough idea of what these integers should be, and then you go through some sort of a smart search to find exactly what the numbers are. And it turns out to be a very tough problem, particularly if you're using a single frequency, because that starts, all those errors that build up in that measurement tend to make the search. There are going to be a lot of possible integer combinations that work for this problem, and it takes a lot of time to resolve them. So one of the challenges with trying to use this approach to solving for centimeter level positioning is that it takes on the order of minutes before you get to the point where you have an accurate estimate of what these integers are. And that does not work very well in transportation applications, because if you're trying to get your position solution and you have to process information for about a minute or more, then that's not a good thing. Now, if you're using two frequencies as opposed to one, then you could actually do this problem fairly quickly, and your uncertainty on these integers reduces fairly quickly. And there are receivers out there that have multiple frequencies and can do this problem. But again, if you're not a DoD authorized user, or you're not have access to a specialized receiver, you can't get these two frequencies, so it becomes a problem to get that centimeter level positioning. The second problem with this is that anytime you lose these signals, same if you're driving your vehicle and you go underneath a bridge or an underpass, you momentarily lose the GPS signal, and when you come out the other side, the integers that you're going to have to solve for are going to be different, because the GPS receiver is actually tracking the carriers and counting the number of cycles that have passed. Anytime you go have a discontinuity, it's going to have to start from scratch. So every time you go under an underpass, you would have to start this initialization problem, and it will take a while to converge, so you can't get that centimeter level accuracy right away. But if you have multiple frequencies, you can actually do that. And the way that, there are a couple of reasons why having more frequencies makes this problem easier. One of the reasons is if you take that signal L1, right, and this is going back to, I guess, basic physics, and you have that second signal L2. In this case, you don't have access to it if you're not a DoD authorized user, but let's imagine you did. Then, if you subtract or add these two frequencies, you could get a new beat frequency that has a wavelength of 86 centimeters. And when it comes to searching for these unknown integers, it turns out to be easier when the wavelengths are larger, right? Because if I'm here and there's a second receiver there, and I'm trying to figure out the number of integer cycles between me and that receiver, if the wavelength is longer, there are fewer that I have to search through. So it turns out to be a lot better if your wavelength is longer. So if you had access to these two signals, then you should be able to do this RTK problem, or the centimeter level positioning initialization, a lot quicker. All right, so again, if you don't have if you're not authorized by the DoD, you can't get to that L2. Now, that's not completely true. There are GPS receivers out there that have access to that, but they do all kinds of special processing, and what it does is they end up amplifying the noise to get to the L2 signal. So, but they're out there, and they're not cheap. They're on the order of tens of thousands of dollars. They're not inexpensive receivers. So, trying to do large-scale transportation applications where you need inexpensive sensors, still not there yet. However, the future is bright. GPS, I guess the system was declared operational in 1995. And since then, there have been several different generations of GPS satellites that have been built and launched. And one of the things that's happening with the newer satellites is we're putting newer signals on them. And one of the things that's happening is the newer signals are going to include signals that are accessible to civilians at different frequencies. So for example, after the original satellites, there was a set of them called the 2RMs that were launched in about 2005. And they started broadcasting a new signal on L2 that civilians have access to called L2C. So now, if your GPS receiver can process that signal, you should be able to do carrier phase positioning accurately, or quickly rather. And then there was another generation of satellite. These were launched, the 2Fs, between 2010 and 2016. Actually, the last one just got launched earlier this year in February. In addition to L2C, they've got a new additional civil frequency called L5. And that one is very much like L1. So now if you have a GPS receiver that's new and that can process the signal, now you have access to 2 civil frequencies. And all the benefits I talked about are available to you. And again, as of 2 days ago, when I checked, there were about 7 of these on orbit. So it's not a full constellation yet, but we've got satellites that are broadcasting out this new civil signal, L5. The plan is in the future, as the satellites get old and new ones get put up, they'll all be broadcasting multiple civil frequencies. And now, the latest and greatest, GPS-3, which is I guess the Air Force decided that it's better to, the 2 other satellites I showed you were basically redesigns, modifications of existing older satellites. GPS-3 is a completely new sheet of paper, new design. And these will be launched in, it keeps on getting pushed back, so I'm not sure if this is still accurate, but first quarter of 2017 is when the first one's going to go up. And these will have a whole array of signals, including a new signal called L1C. So by the time the constellation is completely filled up with these new satellites, the RTK problem should be a lot easier to do. So the centimeter level positioning should be something that will be accessible to most users. But that's not going to happen anytime soon, so it's going to be a while before that happens. But that's one of the things, one of the promises, or one of the nice things that's going to be happening. In the meantime, there are ways of getting the centimeter level accuracy position. One way is to have what's called network RTK. In this case, I'm showing you the version of it that's run by MnDOT, by our Department of Transportation in our state. I showed you RTK on those, or the carrier phase differential GPS on the previous slides. And in that case, the way it worked was there was one reference station, and then there was a user that exchanged information with it. And the network version of it, what you have is a whole network of reference stations. And you, as a user, would send your information into this network. The network will take it, will process it, and will send back a correction to you that makes your position solution very accurate. So this is another way that you could improve accuracy. I mean, our state has a network. I guess many other states have them too. I'm not sure if all states have them, but it's a service that's available, so it allows you to get now centimeter level positioning using GPS. The problem with it is, as you can see right now, this is kind of a sparse network. To get really centimeter level position ubiquitously everywhere, the network would have to be a little bit more denser with more receivers in all the areas. But you can get decent centimeter level positioning using this system here. Now, all right, so in the future, we're going to have all these satellites broadcasting all kinds of various signals on different frequencies. They'll have large networks, so there's network RTK. So are there any other challenges left that are going to prevent us from getting down to the centimeter level of accuracy positioning? And unfortunately, yes, there are more things that we have to get past. And one of them turns out to be something called phase error. So again, drawing a schematic of the problem here, I have 2 GPS antennas, antenna 1 and antenna 2. So this could be a reference station, and this could be a person that's trying to figure out their position. They're looking at the same satellite. All right, and you would think if these two are close to each other, that the noise that they're both going to see is going to be about the same, and it's going to be some sort of a constant, or at least the statistics of it will be a constant. But it turns out that the errors that your measurement has depends on this elevation angle, theta 1, and it varies because the antennas in general are not perfectly designed and their reception patterns are not all symmetric. So that introduces enough of an error that it could actually knock you out of being at the centimeter level of accuracy. Now, with actual data, this is data collected by, trying to remember where it was collected, but it was from one of my students' work a couple of years ago. She was able to show if she had two antennas, very high quality antennas that were basically right on top of each other or right next to each other, seeing signals coming in from the GPS satellites, and you're taking the difference between the signals, you would see that the error, this is number of cycles, as a function of elevation changes. So in other words, those antennas do not have a homogeneous reception pattern. So if you're going to make something that's accurate down to the centimeter level, then you're going to have a decent model of the antenna patterns. For survey grade antennas, they actually do that, and that's why these antennas are actually pretty expensive, right? I mean, your average, I shouldn't say average, but I mean, I do have a survey grade antenna, a couple of them in my lab, and they look very much like this, and they're a couple of $1,000s a piece. They're not cheap because, again, they're very accurately characterized, accurately modeled. So if you're going to put GPS antennas on cars, you're probably not going to put something like this on them. You're going to put something that is inexpensive, cheap. So in that case, you're going to have to do calibration of the antenna itself while it's installed. So until you come up with a way of doing that in situ, you're still not going to be able to get down to that centimeter level positioning. Now, the question is, can that be done? And I think so. And what I want to show you is, without going into the details, here is a slide showing the results from trying to do a calibration of this antenna, of a low-cost antenna online. Here, again, the GPS antennas were being used to measure. I had a pair of them, and I was trying to measure they were connected on a line relative to each other, and I was looking at the angle that was subtended from the horizontal, right? So that's the error of that angle measured by the GPS antennas. And if I just took an antenna out of the box and I tried to do this, I would get errors on the order of anywhere between, it's biased first of all, on the order of 4 degrees, but it could go as high as 10 degrees. And these were errors due to the fact that as the antennas look at signals from the satellites and the elevation changes, the antenna error patterns change. So you get this error that is large. On the other hand, if you did an in situ, if you went ahead and calibrated those errors out while the antenna was installed, you could basically kill those errors and get them down to being really, really small. So, yes, you can get centimeter level of accuracy, but it takes a lot of work. And in the case of really inexpensive antennas, it's going to take a lot of work to get to that point as well. But it's doable. So I guess what I'm trying to say is don't give up on GPS. You can get centimeter level positioning. And it may not happen tomorrow, but it will happen soon, I hope. Anyway, all right. Now, there's another type of positioning technique that's, it's been around for a while, but it's catching on lately. It's called PPP, precise point positioning. And you could think of it as a differential GPS technique, but instead of using a reference station, it's a single receiver on its own, getting corrections from some sort of a service provider that's computing corrections for a global type of a coverage. So they're not looking at differences between receivers, they're looking at absolute positions in this case. So there are services you could subscribe to and get this kind of correction. And the difference between this and the other differential techniques is, again, it's trying to give you absolute position of the GPS receiver on its own, and it involves actually quite a bit of processing. So if you're trying to get centimeter level positioning of a GPS receiver at any point on Earth, there are all kinds of errors that get wiped out or you get ignored when you're doing differential. For example, solid Earth tides. right? So the Earth is actually not static. It's bulging and contracting as the day goes on. As the moon moves around, there are solid Earth tides. You have to actually model them in PPP to be able to get down to the centimeter level positioning, and they do that. The satellite orbits are modeled fairly accurately to be able to do that. So it's a fairly involved process, but once done, it gives you, again, very accurate positioning, and in this case, globally. But again, you'd have to pay a service provider that's coming up with those corrections for you to be able to get down to that centimeter level positioning. The problem with PPP, very much like RTK, there's a really, really long convergence time, and it takes a while before you get down to the level of the accurate position solution and you're moving. But the bottom line is, it's going to be hopefully not very far in the future when we have all these different constellations, all these new satellites with all these new signals, where I should be able to get down to the centimeter level of positioning. All right, so a couple more things to talk about. So the GPS signal itself, right, all these errors add up and take it and prevent you from getting a centimeter level of accuracy position. But there are other things that also play into it, and one of them, particularly with automotive applications, is what you see here. So anytime you go under an underpass or you go into a tunnel, GPS is of very little use because it's either going to be, the signal is going to be attenuated because it's having to go through structure, or it's going to be unavailable altogether. So if you truly want to have ubiquitous centimeter level positioning, you can't rely on GPS all the time. So again, it's more or less now an accepted view that any meaningful navigation system that's going to be giving you centimeter level positioning all the time is going to have to work with all kinds of different sensors. And again, if you return back to that picture that I showed at the beginning, the Google car, that's exactly what it's doing. It's taking a lot of sensors and fusing them together. So again, that's going to be another way to get the centimeter level accurate positioning all the time. But again, it's going to be challenging. By having all these sensors, you're going to get more reliability. You're going to get a continuous, ubiquitous, accurate solution all around. But as you start adding more and more sensors into the problem, you start getting into complex algorithms. And if you're talking about automotive applications where safety of life is an issue, then there's the business of validating and certifying things. And the more sensors and the more systems you have, the more complicated it becomes. But again, this is the route that a lot of transportation systems are going, is multi-sensor approaches where multiple sensors are fused. And that is one of the big challenges right now, certifying and validating systems that are complex like this because they have a lot of pieces to them. So that's going to be a challenge. And again, as we move forward in the future, I said that I used the term GNSS, so now let me come back and talk about all the other different GPSs that are going to be out there. There's GPS, operated by the United States, but there's another operational GNSS called GLONASS, which is operated by the Russian Federation. So it's more or less fully operational now. So if you have a receiver that's able to process both of those signals, then in areas where you may lose sight to some satellites, you'll have sight to the others. So you should have continued positioning. There's another system that's coming along that's being built by China called Beidou, which is going to be another GNSS. The European Union is putting together its own version of GPS called Galileo. So in the near future, it's going to be not uncommon to have many, many satellites in view at any given location. So losing satellites should be less of an issue, and positioning accuracy down at the very accurate level should be available for the most of the time. The other thing that's happening is that GPS receiver architectures are getting more and more complex. This, and again, I'm not going to go into the details of this, but this is your common garden variety GPS receiver, which is called a scalar receiver. Nowadays, with the processing power available on GPS receivers, there are more advanced architectures that are being used. And these advanced architectures, one of the things about them that's nice, particularly this one, is that the more satellites you have in view, all the satellites are used together to basically boost the strength of the signal. So when you go to underpasses where there's interference, these receivers become a lot more stronger or a lot more tolerant to signal outages. So they'll be a lot more robust to interference and outages. Again, right now, for the most part, receivers like this are laboratory curiosities, but it shouldn't be that long when they start becoming standard receivers that are available for commercial use. So, what I wanted to do with this talk was tell you a little bit about GPS and how, or GNSS, and how you could get centimeter level positioning out of it. And again, there's kind of a, I shouldn't say that it's a myth, but I've heard enough people make that comment that that's kind of the motivation for this talk, is that you can't get centimeter level positioning with GPS. It's just not accurate at the centimeter level. It is. It's just that it's not robust and it's not widely available everywhere just yet. The two ways you could get that is by doing carrier phase differential GPS, or RTK as it's called, or precise point positioning. The problem with them these days, they're not robust. It takes a while to initialize them. But again, with the new signals that are appearing, it should be something that is going to be a lot more practical to do. And future developments, particularly the newer GNSSs that are coming and the newer signals that are going to be available on GPS, should make this more feasible and more practical. So with that, I will stop, and I think we have more than, we have 15 minutes worth of questions. So I'll stop here and open the floor to questions. Yes.
Thanks for the talk. With applications like self-driving cars, why is GPS needed to the centimeter level of accuracy if other, I guess, LiDAR or other things can, like within the car, can give it a sense of where it is in relation to other objects?
Okay, so there's actually someone here that could answer that better than me, but I'll tell you at least the why some users want to have GPS. Minnesota is a good example, right? All these systems that you just mentioned rely on being able to see the environment around them and identify markers. If you are in, say, dead of winter where you have a whiteout, in that case, it's very difficult to figure out, get a sense of situational awareness. With GPS, however, because it's a system that's referenced to a larger global coordinate system, you should be able to get lane level positioning in environments where the other sensors would fail.
Any other questions?
Okay, possibly, maybe I wasn't paying close enough attention here. All right, could you just give us a quick rundown? Which of these systems really give you real-time positioning versus which of those will give you centimeter accuracy but only after some sort of time lag?
All right, so let me go to all the different differential techniques. Boom, 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 boom. There we go. All right, so code phase differential techniques, they're not accurate. They're not going to get you down to centimeter level of accuracy, but they're real time, and there's not much of an issue with them, right? Carrier phase differential, or RTK, you can get real-time positioning. It's just that if you're using a single frequency, it's going to take a while to initialize it. And once you've initialized it, anytime you lose track of the signal, you get back to that initialization process again. And it's the same with, right, there's got to be a better way to go with this. PPP is the same way as well. So again, it takes a while to initialize, but once you initialize it, it is a real-time system. It's just, there's that long initialization. The downside with the carrier phase or the RTK approach is that it's brittle. Anytime you lose a signal, and you do lose the signals quite a bit, then you have to go through that initialization again. Now, with multiple frequencies, it's going to be a lot quicker to do that initialization, so it should be real-time and a lot more robust in the near future.
Let me ask one more here then. All right, well, you were talking about one of the ways people are going is this multiple sources of information.
Right.
Could you give us kind of a sense which of these are most effective, okay, in complementing with GPS versus which of these are maybe a little not so good?
All right, I mean, I could tell you about the ones that I know of because I work with them closely, right? So this inertial sensors are by far one of the most commonest, or that's not a word, one of the most common ones that are used with GNSS quite a bit. So these are sensors that measure accelerations and rotation rates. So they complement GPS very nicely. Others that are used, there's mapping along with GPS that's used. Cameras, all kinds of them, along with inertials, are used as well. So that's another combination. The ones that I'm most familiar with and that I work with a lot are these two here, and that makes a very nice combination. And it's, I mean, these days it's almost a given. I mean, even your most basic, like your smartphone, has inertial sensors in it, and they're making use of that and combining it with GPS as well. So.
You said that GNSS might be helpful in timing of the banking transaction, right?
It's used in timing, yes.
Yeah, was it because that different banks was located in different locations so that they have different local time? So it depends on GNSS to tell the accurate local time.
That's
Was
exactly
it the
right.
reason?
Exactly, that's what it does for you. Basically, what you have is a clock that everyone sees at the same time, so everything can be synchronized. So it's a lot easier way of synchronizing clocks. That's why it's being used.
But will the GNSS be more accurate than, I mean, some time recording devices?
What do you mean by? I mean, you could get clocks that are very accurate, like like atomic timing standards that you could use, but they would be local, right? This way, you have a timing standard that synchronizes everyone globally onto the same time base. That's the advantage of it.
Okay, thank you.
So I have two questions.
Yep.
First, do I really have to start saying GNSS, or can I just keep saying GPS forever? And second, with the inertial sensors, are they as real time? Because one of the things we're seeing is, if you're doing transportation and trying to measure a potential imminent collision situation, you have rapid changes and deceleration between units. And so if you have some of those inertial sort of lag, you may not. Is it as real time as what we see with the GNS? And where's the difficulty there?
Okay, so theoretically, inertial sensors should have a higher bandwidth than GNSS, right? So depending on what the sensor is and how fast you're sampling it, you should be able to see high deceleration. I mean, inertial sensors are used on smart munitions, things that are fired out of cannon muzzles, and they're able to keep up with that dynamic. So they are able to measure very, very high bandwidth information. It just depends. The lower the cost the sensor is, probably has all kinds of filtering going on inside it that you're not aware of. But so the basic technology, no, there should be no restriction on that. Should you call it, I think if you were, say, for example, in Europe or in China and you called it GPS, I think they may be offended, right? Because so GNSS is probably the correct catch-all term for it.
Any other questions? No more questions? All right. Well, if you guys can help me thank our speaker. Thank you very much. And next week, we will be having our 8th seminar, which is on dedicated short-range communications. What, why, and how by Imran Hayi. So we will see you next week.